In this segment, we're going to find out what the longitudinal compressive strength of a unidirectional lamina is. So basically what we are trying to do, we're trying to find sigma 1c ultimate of a unidirectional lamina. So unlike our tensile longitudinal strength, we have to look at this particular problem differently because the modes of failure are going to be different. So when you are applying compression, it's quite possible that what's going to happen is that you may get a transverse tensile failure of the matrix or the bond itself. So because if you are applying compression to the lamina right here, parallel to the fibers, then you're going to get tension in the matrix. If you're going to tension the matrix, it's quite possible that the matrix will fail, or maybe the bond next to the matrix will fail. You can get fiber microbuckling extensional mode. You can get the fiber microbuckling shear mode, or you can get the shear failure of the fibers itself when you are applying a compressive load. So what we're going to do is we're going to calculate the sigma 1c ultimate, the ultimate compressive strength, which will be predicted by these four modes, and then we'll take the minimum of those four as the predictor of our ultimate compressive strength in the longitudinal direction. So let's look at the transverse failure of the matrix mode. So what we're going to do is we're going to say, hey, let's go, if we are applying a certain stress sigma 1, which is compressive in nature, to this unidirectional lamina, then the stress in direction 1 will be compressive, which will be given by this formula right here. Then if we use the Poisson's ratio formula, we know that that the strain in direction 2 will be given by the major Poisson's ratio multiplied by the strain in direction 1, negative of that, of course. So we will get this. And from here, we can say that, hey, sigma 1 is nu12 times nu12 times epsilon 2 divided by E1. That's what we're going to get. So what that means is that the ultimate stress which you can apply here will be based on the ultimate strain which it can take in direction 2. So we can basically say sigma 1c ultimate will be equal to nu12 divided by E1 times epsilon T2 ultimate. This will be tensile in nature, so we have to look at, hey, what is the ultimate tensile strain which you can apply in direction 2, or which the unidirectional lamina can take. So we have to somehow come up with the formulas for this quantity right here, so as to be able to calculate what sigma 1c ultimate is. There are some empirical formulas, like for example epsilon 2t ultimate is simply given as the ultimate strain which the matrix can take in tension times some third power or 1/3 power of volume fraction. That's one. Or we can use the mechanics of materials approach, and in that case the ultimate strain in tension in direction 2 is given by still as the function of the epsilon, the strain which the matrix can take, but it is given by this particular formula here. So where you find out that, hey, this is the ultimate tensile strain which the matrix can take. D by S is the diameter of the fibers to the center spacing ratio, and this one is the ratio of the matrix to fiber Young's moduli. So let me write down here, D is the diameter of the fibers, and S is the center to center spacing of fibers. So it's basically dependent on the fiber packing of the fibers in this case. So it could be a square array, it could be a hexagonal array, and so on and so forth. So let's look at the extensional fiber load. We're not going to derive this formula because it's a little bit out of scope of this particular course. So the sigma 1c ultimate based on the fiber microbuckling load is given by a very simple formula. It's given as 2 VF plus 1 minus VF ratio of the fiber and matrix and fiber Young's model I. So here we have simple parameters: volume fraction, Young's modulus of the matrix, Young's modulus of the fiber, and that's about it. Again, let's go and see what sigma 1c ultimate will be if we have fiber buckling shear mode. That again, we're not going to derive it, but it is given by a simple formula. It is GM divided by 1 minus VF, where GM is your shear modulus of the matrix. So very simple formula right here. So let's look at the fourth shear failure mode to calculate the longitudinal compressive strength. So what this is based on is that the composite might fail due to direct shear failure of the fibers. And in this case, if we want to find out what the ultimate shear strength of the lamina is, which will give us this. So it is based on the ultimate shear strength of the fiber, ultimate shear strength of the matrix. So what does this have to do with the ultimate compressive strength? We know that, hey, if we are applying sigma 1c, then the corresponding maximum shear stress which I will get is sigma 1c divided by 2. This we can derive from using the Mohr circle or by using the principal stresses and maximum shear stress formulas. And this will be at 45 degrees to the loading axis, right? And if that is the case, then we can say that, hey, sigma 1c ultimate now will be twice this quantity right here, because that's the amount of shear stress which the lamina is experiencing. So it'll be 2 times what we have written as the ultimate shear strength of the lamina. So we have basically found out 4 compressive strength formulas based on the 4 failure modes. So in order to find out what the ultimate longitudinal compressive strength is, we're going to take the minimum of all these 4 numbers. And that would be the longitudinal compressive strength of the lamina. Let's go and look at an example to find the longitudinal compressive strength of a unidirectional lamina. So we're given a glass epoxy unidirectional lamina with 60% fiber volume fraction. The fibers are circular and in a square array. The Young's modulus of the fiber in the matrix are given. The Poisson's ratio of the fiber in the matrix are given. The ultimate strength of the fiber in the matrix are given. And also given are the ultimate shear strengths of the fiber and the matrix. And what we're supposed to find out is the longitudinal compressive strength of the unidirectional lamina. So what we're going to do is we're going to look at, there are 4 failure modes for compressive strength. So we're going to look at these 4 modes and see which one gives us the minimum value. So let's go and calculate the longitudinal compressive strength based on each of these 4 criteria. So this criteria tells you that sigma 1c ultimate is equal to this expression. So we'll be able to find out the ultimate strength based on this formula. So before we start substituting things in there, we do need to calculate E1, N12, D by S, and epsilon MT ultimate. So if we find those 4 parameters, we'll be able to find out what sigma 1c ultimate is because of this particular failure mode. So let's go and do that one at a time. So what we're going to do is we're going to calculate E1 first by using the rule of mixtures. The Young's modulus of the fiber is 85 gigapascals. Volume fraction is 0.6. Young's modulus of the matrix is 3 gigapascals. Volume fraction is 1 minus 0.6 because that's the volume fraction of the matrix. And that gives us 52.2 times 10 to the power 9 pascals. Then let's go and calculate new one too. Again, we use the rule of mixtures. And here what we're going to get is Poisson's ratio of the fiber is 0.2, volume fraction is of the fiber is 0.6. Poisson's ratio of the matrix is 0.3, volume fraction of the matrix is 0.4 because the volume fraction of the fiber is 0.6, and that gives us 0.24. So let's now calculate epsilon T ultimate and D by S in the next slide. So epsilon MT ultimate, which is the ultimate strain in the matrix, will be sigma M ultimate divided by EM. So that turns out to be 70 megapascals. And Young's modulus of the matrix is 3 gigapascals, so that gives us 0.02333 as the ultimate tensile strain in the matrix. And then we also have to calculate D by S. Since it is a square packing array, then we know that D by S is related to the volume fraction by this formula. So the volume fraction of the fibers is 0.6, and that number turns out to be 0.8740. So since we have all the four numbers which we needed to calculate, let's go and calculate what sigma 1c ultimate will be by using the first mode of failure, which is transverse failure of matrix. So epsilon 2t ultimate is epsilon mt ultimate d by s em by ef minus 1 plus 1. This is what we had. So this one we calculate as this number right here. We calculated d by s to be this number. Young's modulus of the matrix is 3 gigapascals. Young's modulus of the fiber is 85 gigapascals. And eventually this number turns out to be 0.003659. So the sigma 1c ultimate is then given by this formula. And we have calculated all these numbers before. This is 52.2 gigapascals. Epsilon 2t ultimate we just calculated. And new one too is 0.24. And this number here turns out to be these many pascals. So the first mode of failure is giving you the answer as 795.8 megapascals. So let's go and look at the second mode of failure. The second mode of failure is the extensional microbuckling mode. So in this case, our formula turns out to be as follows. It is given in terms of fiber volume fractions, ratio of matrix, and fiber Young's moduli. We have all these numbers available to us right from the problem statement. Volume fraction is 0.6. Young's modulus of the matrix is 3 gigapascals. Young's modulus of the fiber is 85 gigapascals. Volume fraction is 0.6. Young's modulus of the matrix is 3 gigapascals. Young's modulus of the fiber is 85 gigapascals. So having all these numbers here gives us 1.387 times 10 to the power 10 pascals, which is 13870 megapascals. So this is what we get from the second mode of failure. Let's go and see what we get from the third mode of failure. So the third mode of failure is the shear microbuckling mode, And for that, the formula is given as sigma 1c ultimate is GM divided by 1 minus VF. So we got to first calculate the shear modulus of the matrix, which is given by our regular formula for the isotropic materials. Young's modulus is 3 gigapascals. Poisson's ratio is 0.3. So that gives us this as our shear modulus of the matrix. We just substitute back here. We get sigma 1c ultimate is equal to the shear modulus of the matrix divided by 1 minus 0.6, which is the fiber volume fraction. So this gives us a number of so that is 2885 megapascals. The last mode of failure which we discussed is the shear mode failure, and for that the formula which we showed was this one, which is based on the ultimate shear strength of the fiber and the ultimate shear strength of the matrix. So these numbers are given to us. The ultimate shear strength of the fiber is given as 35 megapascals. The ultimate shear strength of the matrix is given as 30 megapascals. So putting in the volume fraction of the fiber in the matrix, which is 0.6 and 0.4 respectively, we get this as our answer, and that is 66 megapascals. So we basically have calculated the value of the ultimate compressive strength here in direction 1 by using 4 failure modes. So we want to find out here what is the minimum of those. So we got 795.8 through matrix failure. We got 13870 because of the extensional microbuckling load. We got 2885 megapascals because of the shear microbuckling mode, and then we got 66 megapascals out of the shear failure mode. So what we're going to do is we're going to take the minimum of these, which turns out to be 66 megapascals. So from the modeling aspect of view, the sigma 1c ultimate is predicted to be 66 megapascals. Now let's go and talk about how we can experimentally find the longitudinal compressive strength of a unidirectional lamina. So the longitudinal compressive strength of lamina is determined by various methods. A highly recommended approach is the IITRI compression test. The IITRI stands for, it's IITRI, stands for Illinois Institute of Technology Research Institute. So they devised this compression test. So you can very well see that, hey, this is where the specimen is, and this is the fixture which they designed to be able to conduct this experiment to find the compressive strength, longitudinal compressive strength of the lamina, as well as its Young's modulus in that particular direction. So these are the specimen specifications for this IITRI test. It comes under the category of ASTM standard D3410, and you can very well see that this is the only amount of this length, which is about half an inch. That's the only amount which is exposed. The rest of this part here, this part right here, although it's a total of 5 inches long, is held in the vices of this IITRI test fixture. So you can see this is 5 inches long and the width is about a quarter of an inch. You also put strain gauges in the front as well as the back in order to make sure that the faces of the specimen are ensured of parallelism of the edges and the ends. So you take about 16 to 20 plies of 0-degree plies. That's what you're going to make the specimen out of it. And the reason why you use many more plies than your longitudinal tensile test is because you want a thick specimen so it doesn't buckle easily, and that's why also the length is small because you don't want it to buckle easily. The specimen is compressed at a rate of about 0.5 to 1 millimeter per minute, which is about 0.02 to 0.04 inches per minute. This particular video which you are seeing here, you won't be able to see the video when you're watching it. You simply go to the particular website which is given down here. It's also given in the project description, so you don't necessarily have to look at the video here. So if you just click on the link in the project description, you'll be able to see that how the IITRI test is set up for the compression test. This gives you some experimental data for the ASTM D3410 standard. And what you do is you plot the compressive stress as a function of the compressive strain. Both are longitudinal, of course. The slope is going to give you the Young's modulus in direction 1, and some people call it the compressive Young's modulus, and that is given here. And then this one gives you the ultimate compressive strength, which turns out to be in this case to be about 1900 megapascals. This one tells you what is the strain at which it is failing in compression. This particular test is done with 24 plies on a graphite epoxy laminate under a compressive load. So you want to use some kind of a linear regression to be able to find out what the Young's modulus is. So you'll have to be able to do that, because that's the initial slope of the stress strain curve which you'll have to calculate. One of the things which you'll find out is that the experimental numbers which you get from the test will be very different from the theoretical results which we discussed. We discussed getting the theoreticals from 4 different modes of failure and then taking the minimum of them, and you'll find out that it'll be way off. It might be underestimated or overestimated based on what you think is happening to the unidirectional lamina. So there are many reasons why people think that the experimental numbers do not match the theoretical results. It could be that there is irregular spacing of the fibers. As much as we like to think that the fibers are placed ideally, that's not the case. So if your spacing is high in certain areas, you get matrix-rich areas, so you won't have premature failure in there. You may have imperfect bonding between the fibers in the matrix. You may have improper alignment of the fibers. Although you think that they are 0 degree plies, they're not perfectly 0. Also, there'll be a Poisson's ratio mismatch between the fiber and the matrix. So have we accounted for that in our theoretical models? And also, many of the fibers in PMCs, they are transverse isotropic. So you can graphite is transverse isotropic, Kevlar is transverse isotropic. So are we accounting for those things in our models? So there is still a lot of research being done in order to be able to figure out that how can we theoretically model the compressive strength of a composite both in direction 1 as well as direction 2. And that's the end of this segment.